Now we move on to pulse Doppler processing techniques, the section range and Doppler ambiguities, and how do we handle them. Here's the chart, the graph, which shows you the line velocity versus the pulse repetition rate, or the unambiguous range of the radar. And it's really the unambiguous range of the radar and the blind speed that we're most interested in. And we talked a number of times about the constraints that this chart puts on us. The constraint between the blind speed, where we're measuring the velocity the radial velocity unambiguously, and the range unambiguously, and they are constrained by this equation. Now, when we send out bursts of pulses and make a set of Doppler filter banks, there are going to be some notches where the blind speed, where we're ambiguous in range and ambiguous in Doppler. And what we do to handle that is a number of things. But first, before I go through those, what I'd like to do is I'd like to bring up the issue of sensitivity time control. We see here a radar, and it's set up to detect a 1 square meter aircraft at 200 miles. And now, because of the signal to noise being proportional to the cross section of the target and to 1 over the art of the and to 1 over art of the fourth, the range to the target, an aircraft, a radar which can see this target at this distance, will also see a bird at 90 miles, 90 nautical miles, which has 1 point, and this is not an unreasonable cross-section for a bird or a couple of birds in a cell. So sensitivity time control is a factor that we really want to be able to use. Now, this false target issue can be mitigated by attenuating the received signal by a factor which varies as 1 over r to the fourth, and we can accomplish this by injecting noise into the received channel, which falls off as 1 over r to the fourth. And then you have a constant signal-to-noise ratio as a function of range. But radars that utilize range-ambiguous waveforms cannot use STC because the long-range targets, which alias down in range, would be very strongly adversely attenuated by the sensitivity time control. And for these waveforms, other techniques must be used to mitigate the false alarm problem due to birds. So that's going to be a limitation on range ambiguous waveforms. Now, this block diagram shows you the relationship between how ambiguous our range measurement is and also for how our radial velocity measurement is as a function of PRF. And we classify in the community radars into low PRF, medium PRF, and high PRF by these characteristics. Airport surveillance radar is unambiguous in range and was very ambiguous in velocity, radial velocity, as you remember, and that would be categorized as a low PRF radar. A high PRF radar would be one that would be classified as unambiguous velocity measurement, but very ambiguous in range. And medium PRF would be ambiguous in both range and velocity. And when we talk about these different classes of radars, they bring up different issues that constrain our use in waveforms or give us difficulty in dealing with different problems in the radar design. Low PRF's radars, a windblown clutter may be a problem. We've shown you how with an MTI system it's a significant problem, and it can be dealt with by sending out sets of pulses and breaking them up into filters at the low PRF, many filters, the order of 10 or so, and then right afterwards sending out another burst of pulses at a waveform whose PRF is 10% different. But depending on the waveform and how we choose that burst waveforms and process it, wind-blown clutter may be a problem. And we can use sensitivity time control, STC, because we're unambiguous in our range measurement. Now, you go to the high PRF mode, and we're unambiguous in velocity, and we're very ambiguous in range. And when you're very ambiguous in range, a large portion of the delay time is taken up by transmission of pulses, longer pulses that might have pulse compression. And there we have an effect known as range eclipsing losses. That is to say, you can't receive information from an echo when the transmitter is turned on. And that can be a significant loss. And distant targets will compete with near-in clutter with high PRF radars. And again, you can't use sensitivity time control because of the ambiguity in range. And medium PRF radars have the difficulties of these, but also the ambiguities are difficult to remove, but they can be removed. So this gives you a big picture description of what you're going to hear a lot of in terms of this is a low PRF mode or a high PRF mode. The radars will mix and match different modes depending on where the targets are, the ones that are multi-mode radars. And so this is to define the classes of MTI and pulse Doppler radars. Now let's move on to the ambiguity resolution problem and talk about the Chinese remainder theorem, a method of resolving ambiguities with multiple when things are ambiguous, when you have send it 3 or 4, 5 PRFs you're sending out to resolve the ambiguities. Okay. First, let's look at the simple case we have of you're only ambiguous in velocity, and how would you deal with that issue? We see at PRF1, we see the real target is out here with its real velocity in red, and when we transmit at a second PRF, a burst of pulses, we see that it's at the same real velocity. But we know from our pulse digital signal processing and aliasing that this block between 4 and 5 folds down to 0 and 1. 1 to 2 folds down to 0 to 1. 3 to 4 folds down to 0 and 1. And the same thing happens for the second PRI. You see there are 2 different pulse repetition frequencies. Only because this pulse repetition frequency is greater than this one, then the true velocity of the target will fold down to a different place in the ambiguous velocity region. Okay, and it's going to fold into a different filter at PRF2 than at PRF1. Now, see, we split the dwell into multiple CPIs, coherent processing intervals at different PRFs, from scan to scan, and even pulse-to-pulse changes are also possible. It moves the blind velocities to ensure detections of all non-zero velocity targets. The PRFs are chosen that way. And the true target velocity is where the best correlation occurs, and you choose the PRF so that the least common multiple occurs above the maximum unambiguous velocity. And the way you do that is you just look down and you'd say, you take this target, which let's just say it's in 1, 2, this is in 3 filter 3, and this is 1, 2, 3, 4. And then what you do is you just unfold, always put the velocities, always putting this detection into its place, where this is n times the blind speed. This would be you'd start the count of velocity bins at 1, 2, 3 at 3, and then this is 4, 5, so you'd start it at 6, 7, and so these are, you'd keep unfolding the velocities after you've done the detections till you see that the detections overlap, and you see out here they overlap, and this can be done in a computer. So for simple cases where there are 2 PRFs, you can see how it's easy to unfold them till you have a match. And then you can say, aha, you multiply this PRF, or total unambiguous velocity, times 1, 2, 3, and then this residue, and that will give you the true velocity, or this 1, 2, 3, 4 times the unambiguous velocity plus that residue, and that will give you the same number as this number for the true Doppler velocity of the target. And now on to the Chinese remainder theorem. Things can get messy when you use multiple PRFs, and this one is the simplest one to go over when you have 3 PRFs, and it's how you use it. It states that the true measured, the real range of the target is a constant times the ambiguous range or Doppler cell number for the first PRF plus this constant 2 times the ambiguous range that you measure with the second PRF plus this constant times A3, which is the ambiguous range or Doppler cell for the third PRF, modulo the product of M1 times M2 times M3. And these PRFs are chosen so that they're relative prime numbers. They're all prime numbers times the same constant. They're different prime numbers. They're all relatively prime times a constant. And so this is the relative prime numbers. And when you take modulo a number, what you're basically doing is taking that number and dividing it by this product, M1 times M2 times M3, until you get a number lower than this prime number, until you get a number that can't be divided by anymore. An example would be if this was modulo, if you wanted to calculate 1 modulo this number, and this number was 9, well then 1 modulo 9, you get a number 8. What it is that and you'll see it in the example a little better. The C1s and the C2s and the C3s are related to M1 and M2 and M3 by the constant is equal to B1 times M2 times M3 equal 1 modulo M1, where B is the smallest integer which, when multiplied by M2 times M3 and divided by M1 gives unity as a remainder. And this is the equation for getting the C's, and you can get the B's of the smallest positive integer which when multiplied by these numbers give these numbers as remainders. Now let's move to the example of just the 2-PRFs. Here we see a Doppler filter bank that has 8 filters, then another 8, and then it goes on and on and on. And here we have one with 5, 5, 5, and on and on and on. And we see we detect the target in filter 5 at the first PRF and filter 3 at the second PRF. And for ease, I've picked nice round numbers. 5 and 8 are relative prime numbers. The blind speed for the first PRF would be 80 knots. 10, 20, 30, 40, 50, 60, 70, 80. And for the second one, the blind speed would be 50 knots. Each filter of 100 hertz is 10 hertz wide for an S-band radar. And then, so to calculate RC, we need to, if you reduce that 3-PRF system, you come out with C1 times A1 plus C2 times A2 modulo 40. And this would be modulo M1, M2, dot, 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 dot. But there's only 2, so 8 times 5 is a 40 there. And the A1s are 5 and 3. And using the arithmetic over here, we can calculate the B's as 5 and 2, and we fill those in with these numbers, and we get 173 modulo 40. So all you basically do is you just divide 40 into 173 till, if you divided it again, you'd get subtract it, excuse me. If you subtract 40 out of 173 and keep subtracting it till just before you get a negative number, you can subtract it 4 times, 160, and you're left with 13. And this is in units of filters, which you have to multiply by 10 to get the knots. The true velocity is 130 knots. And you can see if you count up each one of these are 10 wide, 10 knots wide. This is 13 filters up, and this is 13 filters up, which gives you the true velocity of 130 knots. And this can work even into up to PRFs of 4. And what I'd like you to do is so you learn the theorem is, and I've shown you what the length is just in calculating B1 for the first C. But let's present the problem first before we talk about the solution. Just imagine you're in a room with 3 people as completely ignorant as I am, and I call them Larry, Moe, and Curly. So we've got Bob, Larry, Moe, and Curly. And we have shoes on. And my shoe length is exactly 7 inches. Larry's is exactly 8 inches. Moe's is exactly 9 inches. And Curly's is exactly 11 inches. Notice they're all relatively prime numbers. Now, we're kind of slow, and our memories aren't so good. And when you come to think of it, it turns out I have an illness called chronic fatigue disorder, which really does a number on my short-term memory. And so I really fit into this category of the problem we have here. We each put our feet one in front of the other, like, you know, you're in a room and you want to see how long it is. You go, you count, you go 1, 2, 3, 4. You get up the end and you count off how many inches you've got left in your shoe, the remainder. And by the time I count that I've got 2 inches left in my shoe, I forget how many times my shoe went, that multiple times. I only remember the remainder. And the same with Larry, Moe, and Curly. We remembered our remainders, but we forgot, and we know how long our feet are, but we all forgot how many times it took us to get to that short remainder. And you can use that use the Chinese remainder theorem for dunces like moi to figure this out. And so the length of the room is just this. It's got an extra. It's modulo M1, M2, M3, and M4. And the product of all the different M's is 5,544. And I want you to just, by yourself, go through this arithmetic, learning, what the modulo is. Think about it. And you can calculate, and I want you to do this not just for C1 and B1, but I want you to calculate for the whole what the lengths are. And in other words, I want you to calculate these numbers here and prove that the length of the room is 149 inches. But anyway, calculate the numbers and see what you come out with. But go through this arithmetic yourself as a problem if you want to learn how people unravel PRFs. And at ambiguous medium PRFs, this is what's programmed into the computer, and it's something that you can easily program. Okay, and now on to the ambiguity function.